section 6.1 talks about power series and functions. So here's the deal. In the previous section, we figured out whether the series converge or diverge, and using what test and so on and so forth. And toward the end, we start talking about this kind of like, for what values of x does it converge. Now, in this chapter, we're going to take every relation in math that you can think of and write it as a power series. That's the goal. We start off by saying, look, if you look at a series, n equals 0 to infinity of c sub n x sub n, substitute n equals 0, that's c sub 0, x to the 0 is 1, c sub 1, assuming that x doesn't equal 0. Let n equal 1, then you get c sub 1, x sub 1, c sub 2, x sub 2. So this looks, if you really look closely at it, it looks like a polynomial. And this x is going to pretty much come out with the varying part, and those c's are the coefficients, they're constants. So when we talk about domain in functions or relations, it's kind of like what we're going to do here, except we're going to figure out for what values does this series converge, what values of x, and we're going to call that kind of the domain, like, this series converges for these values. So as long as x is between such and such values, we are safe to use the series, otherwise the series diverge. And this is the same as that, except you're shifting everything by a. This is like me saying this is y equal x squared, and this is like y equal x minus 2 squared. Just shifting, nothing more. And we say this series is centered at a, just like we say this parabola is shifted 2 units to the right, or centered at 2 as well. All right, and that's the idea of this. Now we're going to start with, there are 3 main ways that you could write any relation as a power series. Oh, let me rephrase. There are 3 main ways we're going to write the series that we are given as, the relations that we are given as power series. First, and the most crucial, you would save yourself a lot of time if you recognize a geometric series. This is the series n equal 1 to infinity of x to the n. Well, let n equal 0. X to the 0 is 1. X to the 1, x to the second. Notice you're multiplying by x every time to get the next term. So this is geometric. And this is infinite sum. Since it is infinite, this geometric sum would be the very first term divided by 1 minus r, which is, the very first term is 1 over 1 minus x, provided absolute value of x is less than 1. That's kind of like the domain. And now that we know this, well, guess what? Anything that looks like this, I can write backwards. I can write as a power series n equals 0 to infinity of x to the n, assuming this is less than 1. And if this is bigger than or equal to 1, and keep in mind, I'm sure you remember that. That's what that means. That means x is between -1 and 1. So if x is 1 or greater, -1 or less than, then that diverge. Keep in mind, I need a 1 there. I also need a 1 there. And I need a minus, and this is the key. That x is that x. So if I'm able to write any relation that I get looking exactly like this, I can write it as a power series. That's 1 out of 3 techniques we're going to use to write any relation that they give us as a power series. Now, they are going to give us those in stages, and at the end you kind of put everything together. Well, let's see how this goes. It says in the following exercise, suppose that this limit equal 1. Okay, all good. As n approaches infinity, very good. Find the radius of convergence. So in this case, I'll say this is the radius of convergence. The radius of convergence is negative 1 to 1. And note here, I do not need to test the endpoints like we did in the last section, because I know from geometric series, if r equal 1, if you multiply by a number that's 1 or bigger, the series diverge. So if I'm using the geometric series, I simply figure out what r is, come up with an inequality, and that would be the interval of convergence, and no need to test the endpoints. But there's r. R is 1 in this case. Let's look at this problem and work it out. This is problem number 8. I would like to figure out the radius of convergence. Anytime they're going to ask me to find the radius of convergence or the interval of convergence, either I'm going to be looking at a power series, and I would use the following analogy, and whatever I substitute in for x, I set that to be less than 1, and that is my radius of convergence. Done deal. Well, let's look at this problem. This is not geometric. The only other alternative is either geometric, or I use what we did in the last section. I take the limit as n approaches infinity, and that's going to be a sub n plus 1 x to the n plus 1 over 2 to the n plus 1 divided by a sub n x to the n over 2 to the n. That is the limit as n approaches infinity, and that's going to be a sub n plus 1 x to the n. Okay, that doesn't look like what do you call it? What's the word for the subscript? And that is 2 to the n, 2 to the 1. Instead of dividing, I'm aware you're already used to that, but just the first example, I want to work out in full steps. After that, I'll start jumping the steps straight. Well, the x to the n's cancel out. The 2 to the n's cancel out. I have the limit as n approaches infinity, a sub n plus 1 over a sub n times x over 2. And they told us that, hey, this limit is 1. So I am aware that I would be left with the limit as n approaches infinity of x over 2. And that's independent of n. That's x over 2 in absolute value. Now what do I do? If it was geometric, that would have been easy. Since I'm using the ratio test, anytime I use the limit as n approaches infinity of a sub n plus 1 divided by a sub n, either I'm using the ratio, right? I could also use the root test if it benefits me, but mainly the ratio. Then what I'm going to do, I'm going to take this quantity that I got and set it to be less than 1, because that's what the series restricts. Now, in this book, they solve for x all the time. Once you get the absolute value of x on one side, everything else on the other side, you call that the radius of convergence. Now, as far as radius of convergence, we're done. All what you have to do is figure out what that is. If they were to say test the interval of convergence, so this is a note that you don't need, then you would say, well, this means that x is between -2 and +2. Then I have to test if x equal -2, what happened? If x equal 2, what happened? This is for the interval of convergence. I do that because this is not geometric. If it was geometric, I would never ever test the endpoints, because I know in geometric series, if this value equal to 1, the series diverge. And that's pretty much it. So here they're asking for the radius. Get x by itself and everybody's happy. Now I could go by and show you. If you are to say absolute value of x over 2 is less than 1, if you say this equal r, the intervals will be the same, but we're not going to do that. So that our answers will match, we're going to go by literally x every time and call that the radius. And this way everybody's happy. Same deal here. This is, again, I don't know what a sub n is, so I don't know if this is geometric. We're going to use the ratio test. Limit as n approaches infinity. Now here I could use the root test if I want it, because I could say that's -4x squared to the n, take the nth root of that. That works as well. It's up to you. Doesn't really matter. So I could show you both. Limit as n approaches infinity, a sub n plus 1, negative 4 to the n plus 1, x to the 2 into n plus 1. Instead of multiplying, I'm going to divide by a sub n, negative 4 to the n, x to the 2n. That is the limit as n approaches infinity. Well, I am aware that this is a ratio of 1. That is negative 4 to the n, negative 4 to the 1 over negative 4 to the n, x to the 2n. This will be x to the 2n, x squared. These cancel out, these cancel out. I am left with the limit as n approaches infinity of negative 4x squared. And if I take the limit as n, there's no n in there. That is negative 4x squared. Set that to be less than 1, which means if I divide by, that's really 4x squared less than 1, divide by 4. And if I look at the square root, so the deal is to get this to be x, call that r, everybody's happy. I just want to point out, you could have easily said take the limit as n approaches infinity of the nth root of, and remember how that works? Oh, that wouldn't work because they didn't give us the coefficient, you know? This will work for this. So you could say that is a sub n, negative 4x squared to the n. That's the limit as n approaches infinity. So this cancels with that. You're left with this. But we need a sub n plus 1 over n to really work this out, because they didn't tell us what a sub n is. They just gave us that condition. But that's all good. That works. Well, there it is. Now what? Now find the radius of convergence and the interval of convergence. Remember, the benefit of using the geometric series, the interval is given away right away. I don't need to test the endpoints. Glancing at this, so I'm looking at n over e to the n. That's not geometric, unfortunately. I'm going to take the limit as n approaches infinity of a sub n plus 1, n plus 1, x to the n plus 1 over e to the n plus 1. Instead of dividing, I multiply by the reciprocal. That is the limit as n approaches infinity of n plus 1 over n times x to the n times x to the 1 over e to the n times e to the 1 . This is 1 plus 1 over n. As n approaches infinity, that approaches 0. So pretty much I am left with x over e in absolute value. Set that to be less than 1. So this is what I'm getting. I'm getting absolute value of x is less than e. There's my r. So it says find the radius of convergence. I did. Interval of convergence. Well, if I used the geometric series, I would have said simply the interval of convergence is really x is between negative e, and everybody's happy, right? So simply negative e to e, and I would use parentheses around it. But since I did not use geometric series, I'm going to say, okay, let's test. What if x equal negative e, the left endpoint? Look at the series. The series would look like the series n equal 1 to infinity of n negative e to the n over e to the n. That's the series n equal 1 to infinity of n negative 1 to the n e to the n over e to the n. That's the series n equals 0 to infinity of negative 1 to the n times n. The limit as n approaches infinity of n equal infinity, not 0, or you could say it does not exist because of oscillation. Therefore, diverge by divergence test. So in this case, I know for sure x gonna be negative e. I'm certain that's parentheses. I'm not sure about that, and I would test it. Let x equal e. Again, this series become the series n equals 0 to, oh, n equal 1. Apologies. I've been putting zeros. My mistake. N equal 1 to infinity of n e to the n over e to the n. That is the series n equal 1 to infinity of n. Again, take the limit as n approaches infinity of n equal infinity, not 0. Therefore, diverge by divergence test. So I can't have that either. That is the radius of convergence, and that is the interval of convergence. Sometimes both ends don't work, sometimes both end works, and sometimes one work and the other work. There's no set way of figuring this one out. Without the testing, it's not possible. And even if you're able to figure it out, you have to show all of that work. Here's another example. I'm looking at this series. Well, I'm going to take the limit as n approaches infinity of a sub n plus 1 divided, so you multiply by the reciprocal, this is bigger than that, so you start reducing n plus 1. The next one will be n. Limit as n approaches infinity of x over n plus 1. That limit is 0, which means it's less than 1 for all values of x. So this limit, as n approaches infinity, x is a constant, that's going to approach 0. It's going to always be less than 1, right? Therefore, we say r is infinity. Remember what r is, the values you could choose. R is infinity, there's no bound on this. And the interval of convergence is negative infinity to infinity. Any values of x will satisfy that case. Now, let me just elaborate really quick. When you say the radius is e, so the radius is 2.7, you could go above or below by 2.7. Normally, you would do this work because this is not always centered at 0. Remember what we said. Certain are centered at 0, some are not centered at 0. Knowing what e is, well, you need to know where are you starting, and that's why we just do the algebra and get it out of the way. This way you don't have to memorize all of these cases. If the limit is always less than 1, this series converge for any value of x. That's kind of like you're saying, oh, domain is all real numbers. Versus here, you're saying the domain is, make sure that between negative e and e, not inclusive. And how about this problem? Here we're going to take the limit as n approaches infinity. Okay, this is going to be, and here we're going to have to work a bit slowly at this, 2 into n plus 1 factorial x to the n plus 1 over n plus 1 to the 2 into n plus 1 multiplied by the reciprocal x to the 2n over 2n factorial x to the n. Now, if I was you, I wouldn't really assume anything about factorial properties and play with them. Gotta be really careful with factorial. This is 2n plus 2 factorial. So this is the goal. I'm going to start reducing this until I get exactly that. So that is 2n plus 2, subtract 1, 2n plus 1, subtract 1, there it is. That is x to the n, x to the 1. This is 2n plus 2, so that is n plus 1 to the 2n times, oh, okay, I made a mistake, I'll fix it, times n plus 1 squared. Okay, I wrote this one wrong. When I multiply by the reciprocal, 2n, okay, if I take the reciprocal of that, that's x to the n, and that is x to the 2n. No, that's n to the 2n. Just not used to writing that so much. Here we go. times 2n factorial x to the n to the 2n. Okay, well here, these two cancel out. And the limit as n approaches infinity. I'm going to factor a 2 out of that. Oh, and these cancel out. That was why it reduced it. Now, I'm going to take these two and combine them into one. And on the bottom, there's n plus 1 squared. Let me make sure I did not leave anything out. Okay, it looks like we're okay. That is the limit as n approaches infinity of, and let's see what that is. One of those cancel with one of those. 2 into 2n plus 1. So that is really 4n plus 2 over n plus 1 times x times 1 divided by 1 plus 1 over n raised, oh boy, this is not going to work. Okay, this is what I'm going to do. I'm going to take the reciprocal of that. If I divide by n both of those, so remember, instead of using L'Hopital, you could do that. And here, I could say that's 1 plus 1 over n to the negative n squared. To save time here, only in this chapter, chapter 6, I could say this is e to the 1 to the negative 2. So here I could say in this chapter, in this section only, chapter only, limit as n approaches infinity of 1 plus a over n to the n is e to the a. In other sections, you have to show that using L'Hopital. So what am I getting altogether? I'm getting 4 over ex in absolute value. I want that to be less than 1, which means absolute value of x has to be less than e over 4, which e squared over 4, which would be my radius of convergence. Oh boy, there's no room to do the rest. Okay, well, I didn't copy directions. I have them now. Here they are. It says in the following series, find the radius of convergence of each, just the radius. You don't have to worry about the interval of convergence. Let me just check how many more problems we have. 1, 2, 3, 4, 5, 6. Okay, let me make another video so I do